you so much, Max, for the introduction. Thank you so much for the organizers for organizing this conference. I want to say, as I'm sure many people have said already, I'm very sorry I couldn't be there in person. I really wish we could all have been together, but well, at least there is a way for us to keep some of the proposed activities. I apologize, I have a little dog here at home who has just seen a squirrel. So very exciting, much more exciting than the almost minimizers, I guess. So before I get into this almost minimizers for the specific obstacle problem I want to describe, I'm going to talk to you a little bit about what motivates that problem, or where does it come from something that some might be more familiar with. So let's make sure I can move my slides indeed. Okay, so let's start with our beloved boundary value problem. Let's say the Dirichlet problem for the Laplacian, an operator that I'm sure all of us know and love. So we have a domain omega in our N. Let's say we have a function phi continues on the boundary, that is our boundary data. And let's say I have a function f in some nice space, which is going to be the right-hand side of my PDE. And I want to find a function with some, regularity in such way that this function satisfies a PDE inside of the region and has the boundary data phi on the boundary of this domain. That's a boundary value problem. I want to notice that the solution of this problem can be seen as the minimizer of a certain energy. So in this case, solving this problem is the same as looking at the energy that I'm calling J over here, which is related to the Dirichlet energy. So we have here the gradient of V squared plus 2FV, and we want to minimize this energy among all functions with a certain boundary data, in this case, phi. So a minimizer will exist and it will solve our PDE. So let me give you a nice simple example in R. Let's say we have a simpler energy even, so I just have the integral from 0 to 1 of V prime squared. And I want to minimize this energy among all functions that are equal to -1 at 0 and let's say 3 at 4. As you can tell, I randomly chose these numbers. Then in this case, you can actually compute this by hand, and you will see that the minimizer will be equal to x minus 1. It's linear, and it's harmonic. So the Laplacian is 0 inside of the domain. Now let's tweak this to make things a little bit more interesting. What if not only I have boundary requirements, but I also require my function u to be above something else, a given function? This is going to be an example of the classical obstacle problem in R. Let's preserve the energy. So I have the integral from 0 to 1 of V prime squared. I still have the same boundary requirements, so -1 at 0 and 3 at 4. But now I put a obstacle that happens to be a parabola in this case, just because it's much easier to draw the picture. And I want to find a function that has the boundary data and it is greater or equal than this function in blue, the parabola, inside of the domain. And in this case, you can also compute what this minimizer is going to satisfy. And it so happens that the minimizer will be equal to those two lines we had in a certain region close to the bounds of the domain. And in the middle, in the region in which that line was actually crossing the parabola, we are going to be actually the parabola. So here you will notice that the minimizer that we end up is the one that I drew in blue in the picture, happens to still be harmonic in the region in which the function is strictly greater than this extra function I put, which is what we're going to call the obstacle. So the obstacle would be the parabola in this case. So the classical obstacle problem is that in R, and it is an example of a free boundary problem. More generally, we have this energy, so the Dirichlet energy plus, so the gradient of V squared plus 2FV, and we want to minimize this energy among all functions with prescribed boundary data, which are, in this case, let's say the obstacle is 0. So which are greater or equal to 0 in the whole region U. This is a free boundary problem, which means that to solve this problem, we have to find not only the function u, a minimizer, but also what is the free boundary, which is the boundary of the region where the function is strictly greater to 0. And the reason why we're so interested in this is if you look at the previous example, that's the region in which things change. We went from being harmonic to coinciding with the obstacle. So we're very interested in understanding that boundary, the free boundary. We can also rewrite our problem in terms of a PDE. So here we can write that the minimizer we obtain is going to satisfy that its Laplacian is equal to f times the characteristic function of the set where u is positive. So the Laplacian will be 0, where u is actually equal to 0, and it will be f when u is positive. And we also have the requirements that u is greater or equal to 0. So here, let's look at the picture. In this particular picture, I'm thinking in R2, so you're going to have not a problem, but rather more like a mountain. Great picture. Imagine the mountain right behind me. And you're going to have a region where the minimizer is equal to the mountain, and then a region in which they detach. And that will give you different PDE requirements. So the study of this obstacle problem began in the 60s with works of Stampacchia, Lewy, and Lyons, and it has led to really, really nice developments in calculus of variations and geometric PDEs. One of the beautiful achievements of this study has been the development of the theory of free boundaries by Caffarelli and many others. And nowadays, people are still very interested in obstacle type problems. We still have a lot of different people working with variations of this in the context of minimizers, or, as I'm going to talk today, almost minimizers. So in particular, I want to focus a little bit on the thin obstacle problem, or called Signorini problem. Today, I will talk a little bit about the minimizing problem and then the corresponding almost minimizing problem that arises from that. So just recap, what was the classic obstacle problem? You have an obstacle defining the whole domain. You have boundary data. You have a function f, the right-hand side of your PDE. You want to minimize an energy over all functions that have boundary data and are on top of the mountain over the obstacle almost everywhere in the domain. So our mountain here, you're going to have the boundary data. You're going to have a region in which the obstacle is equal to the minimizer and a region in which they detach. The minimizer is strictly greater than the obstacle. With respect to our previous picture in 1D, let's remember here the blue graph is the graph of the minimizer. The obstacle is the one in red. There is a region in which they coincide. The boundary of that gives us the free boundary. And that's going to tell us that we have this dichotomy in the behavior of the minimizer u. In the region where it's strictly greater, the minimizer will be harmonic. And then you have the region in which they coincide. So you start with a minimization problem. You show that there is a unique minimizer. This unique minimizer satisfies the PDE that you wanted. So it will be Laplacian of u is equal to f, where they are not equal, where u is not equal to the obstacle. And in the region in which they are equal, their Laplacians will coincide almost everywhere. Very important, we have these two sets, the coincidence set, which is the set where the minimizer is touching the obstacle. So just a second, in my previous picture, this would be this upper portion where they're really touching. And then we have the boundary of that region, which is what we call the free boundary. So we're very interested in understanding what happens with the free boundary. So initially, you might ask yourself, I can pose this question in a very weak sense. So how actually smooth is a minimizer that you find? And it turns out that the optimal regularity is C11 in the case of the classical obstacle problem. So your minimizer will be W to infinity log. With respect to the free boundary, things can become quite interesting. In the case of the obstacle problem, in 77, Kinderlehrer and Nirenberg proved that if you know the free boundary is C1, it has to be real analytic, actually. And around that time, Caffarelli was working on his theory of regularity of free boundaries, and he was able to prove that if you are flat, so if your free boundary is at every appropriate scale squished between two planes, let's say, then it has to be Lipschitz, that is the graph of a Lipschitz function. And then if it is Lipschitz, it actually has to be C1 alpha. So if you combine all of these results, you are able to show that if the free boundary is flat, it has to be real analytic. So the best that you can hope for. Now let's get into this thin obstacle. And as I mentioned, I want to talk to you about the minimizing problem first, because that will give us a little bit of understanding of what is going to be different for almost minimizers and how the techniques can or cannot be applied. So in the case of the thin obstacle problem, instead of having an obstacle defining the whole region, I'm going to have an obstacle defined on a portion of the boundary. So in this case here, the kind of orangey part of the picture, this would be the region that lies below the graph of the obstacle. So the obstacle is defined on a portion of the boundary. Let's say that our domain is the upper unit half ball. D. Okay, just here things are local, so we don't have to worry about what exactly was the initial region. Let's say that our manifold M is the flat portion of the boundary of that region, the one that I'm drawing here in blue. And in general, this is going to be an equal dimension one manifold. I'm going to have an obstacle defined in the blue part, and I'm going to have a function psi, which is going to be the boundary data in the remainder of the boundary. Let's say we want to minimize the Dirichlet energy over the convex set of functions that are equal to psi, the boundary data on the curved portion of the boundary, and which are greater or equal to the obstacle on the flat portion. Now the situation is quite different because the obstacle itself is not on the whole region. You don't have a mountain. You have more like a wall, if you want to think of it that way. So where does the thin obstacle problem appear? First of all, this was developed by Signorini. That's why this is called the Signorini problem as well. And he posed this problem in the context of elasticity. So if you have an elastic body at rest, laying on a surface M. It also models the flow of a saline concentration if it's going through a semi-permeable membrane. This is in the context of osmosis, in the context of the parabolic Signorini problem. And it can also model the random variation of an underlying asset that changes discontinuously in the context of American options. So it has some applications in math finance. Let's go back to our math problem and let's look at the fact that we had initially a problem defined on a half ball. As many people have discussed, we have sometimes some energies that we can play with that are defined on balls, for example, the Almgren monotonicity formula. That's something that we want to apply. Actually, I'll talk more about that. But because of this, it's quite inconvenient to have a region that is not symmetric. So for that, we initially have a half ball. We extend our minimizer evenly, and we extend our boundary data evenly. I want to notice that this, which seems rather innocent that I'm doing right now with minimizers, will turn out to be a huge problem for almost minimizers. So just a brief comment that I will get back to this later. So in the context of minimizers, we simply take the even extensions. We have a wonderful almost minimizer of this other energy in a full ball, and we are happy. And this is the one that we work with in the case of minimizers. So now the picture looks more like this. We have this thin manifold lying inside of your region, and only there you have an obstacle defined. You also want to generalize this problem, and I'll say a brief few words why. So instead of looking at the Dirichlet energy in which the operator is the Laplacian, you might want to have a divergence form operator with variable coefficients. The reason for that is the following. Many times your obstacle is not flat, as in the case of the picture that I had before. However, if it's nice enough, if your manifold is nice enough, you can locally flatten it. But once you flatten it, your operator changes. So instead of having the Laplacian, you will end up with a variable coefficient operator. For that reason, we wanted to look at this energy instead, because then it will take into account the situations in which the manifold was not flat to begin with. So I have a matrix A that I'm going to assume is symmetric, uniformly elliptic, has Lipschitz coefficients, and at the point 0, it's equal to the identity. So here now, our class of candidate functions is exactly as before, but we have this matrix to take into account. As in the case of the classical obstacle problem, we have a coincidence set, which is the set of points where the minimizer is equal to the obstacle, but do notice this is a set that lies inside of our manifold, our thin set. And then we have the boundary of that set in the relative topology of the manifold, which is what we call the free boundary. And for now, let's say we assume that the obstacle is C11 defined in this thin set. Because we have minimizers, we can look at what are the Euler-Lagrange equations of these minimizers, and you will end up with some nice conditions. These are the ones we call Signorini conditions. So first of all, you have a PDE, which makes you smile. You have techniques from PDEs to use. At least it makes me smile. I don't know about Max. He's laughing there. So let's say we have the divergence of A gradient U, and this will be 0 on the upper part of your region and on the lower part. Then you will have certain conditions that are true on the thin space, which is the space in which you have to worry about the obstacle. Okay. So as I mentioned, there were a few things that were true for minimizers and they won't be true for almost minimizers. This slide is another one of those examples. Our almost minimizers that will come soon are not going to satisfy these equations. That will pose a lot of difficulties. So in terms of the regularity of minimizers, there is a work by Caffarelli from 1979 that proved that if your manifold is a hyperplane, the obstacle is C2 alpha for some alpha between 0.5, and the coefficients of your matrix are C11, then your minimizer has to be C1 alpha on the upper part of your domain until you hit the manifold, and on the lower part until you hit the manifold, not across, because actually it is not C1 alpha continues across. Then Arkhipov and Rautseva had a couple of papers between 85 and 87 in which they obtained the same conclusion, the C1 alpha conclusion, assuming the coefficients of the matrix are in W1P and the obstacle is in W2P for some P greater than N. So in particular, this includes the case in which the coefficients of the matrix are locally Lipschitz, which is the one that I'm talking about at this moment. Then what about optimal regularity? So even if we don't have to worry about this matrix, so even if the operator in question is the Laplacian, even if the manifold is flat and the obstacle is 0, the best you can do is actually C1 1/2. And the reason for that is we actually can compute explicit global solutions in that setting. And that minimizer is the real part of x1 plus ixn to the 3/2, and that's the regularity you get. So then the question becomes, can I prove this optimal regularity for any minimizer? And the answer will be yes. So first of all, in the case of the Laplacian, Athanasopoulos and Caffarelli were able to prove this in the case in which the manifold is flat and the obstacle is 0. Richardson had proved this result, but only in dimension 2 previously using complex analysis. This was, I guess, the first thing I've ever done in math was to prove the optimal regularity, assuming that the coefficients of the matrix were locally Lipschitz. So that is also true, assuming the obstacle is of class C11. In 2016, using very different methods, Ankana Ruland and Wenhui Shi proved also the C0 alpha regularity, assuming that the obstacle is in C1 alpha and the manifold is flat. And they used Karleman estimates, so very distinct methods here. In terms of the free boundary, there's many interesting things to be said and still many things that are still unknown. So let's recall that the free boundary is the boundary in the thin set of the region where the minimizer is equal to the obstacle, boundary of the region where they are touching. So I will just briefly describe what has been done in terms of the regular set and the singular set. And of course, if we have to split the free boundary, it already tells us that things will be more complicated. So one of the important techniques we use is the monotonicity formula of Almgren. So in the case in which we have a beautiful harmonic function, let's say in a unit ball, you can define this really nice function, the frequency. It's a function of one variable. And you can prove that this function will be increasing as long as the function u was harmonic. Furthermore, this frequency will be constant if and only if u is homogeneous of degree kappa. And it turns out that in this format, this is not true for almost minimizers or minimizers, but one can adjust this a little bit and obtain an almost monotonicity formula that happens to be not only extremely important for the regularity results of what is the regularity of a minimizer, but also in terms of classifying free boundary points. So you look at the limit of this function as your radii goes to 0, if you're looking at balls centered at different points on the free boundary, and that allows you to classify the free boundary points. So the generalization that you do in the case of minimizers for the Signorini problem, in which you have a variable coefficient, you have to tweak that frequency formula a little bit. You also have to multiply it by an exponential term, which looks pretty terrible, but we're only interested in what happens as r goes to 0, so this is harmless. And this function is monotonic. Not only that, well, it's also greater or equal than 0, so it has a limit as r goes to 0, and that is crucial for us to classify points in the free boundary. So you pick a point on the free boundary, you do a change of coordinates so that you shift it to 0, you call the corresponding frequency function n of x0, and the limit at 0 is called the frequency at that point. So that number, the frequency at the free boundary point, can be used to classify points on the free boundary. And then you're also interested in understanding what are the possible values that this frequency can take. So first of all, this was important. We were able to prove that that number, the frequency, is either 3/2 or greater or equal to 2. The fact that you have this gap in between the frequencies is crucial in the study of the points of the free boundary for which the frequency is 3/2. Those are the ones we call regular. And then you're interested in understanding what happens with the other ones as well. And also what numbers can actually appear. So in dimensions 2, you can show that the possible values you have are 3/2, 2, 3, 7/2, 4, 5, and so on. So you have m, 2m minus a half, and 2m. Then a paper by Spadaro and Focardi from 18 showed that in dimensions 3 or larger, the same is true up to a set of Hausdorff dimension n minus 3. So that's the other set. And it's quite interesting that we know very little about this other set besides a bound on its Hausdorff dimension. Let me say that the set of points on the free boundary for which the frequency is the smallest possible, 3/2, is called regular. Those are the best ones. And the reason why they're the best ones is this series of results. So in 2008, Caffarelli, Salsa, and Silvestri were able to prove that the regular set, in the case of the Laplacian, is locally a C1 alpha regular n-2 dimensional surface. Then in 2016, we used a Weiss monotonicity formula that is used for us to kind of zoom in what happens in a point on the free boundary. And we also used an epiperimetric inequality to show that the same holds, assuming that the coefficients are locally Lipschitz. Then using Kahneman estimates, Koch, Ruland, and Shi were able to prove the same result, assuming the coefficients are in W1P for P greater than 2n. Then you can actually continue the study and prove that if you are C1 alpha, you actually have to be C infinity. So the regular points on the free boundary are really fantastic, which leads the question to, first of all, what happens with the singular set? And we can say some things about this. And also, what happens with the other set, the points that are neither regular nor singular. And that is a more complicated question. So in terms of the singular set, there is something interesting that happens, which is we start by defining the singular set as the collection of points on the free boundary for which the frequency is an even number. And it turns out that this leads to very important facts about those points. I also want to mention that instead of defining them this way, you can also define them as the points on the free boundary for which the coincidence set, which is where the two, the minimizer and the obstacle touch, so where the coincidence set has vanishing n-1 dimensional Hausdorff density. What does that mean? This is what it means. So you have a limit of these two quantities. So you look at the measure of the coincidence set in a thin ball divided by the measure of that thin ball, and this quotient has to be 0. It has to tend to 0. So these two things happen to be equivalent, having an even frequency and having this 0 Hausdorff density. And with that, you can actually do several things and prove several things about these points, the singular points. So for this part, let me say, I'm just going to assume the obstacle is 0, otherwise the formulas become quite hairy. The first thing that you do in the case of the Laplacian, you can actually do other monotonicity formulas around those singular points, and you're able to prove that the singular set is actually inside a countable union of C1 manifolds of certain dimensions, dimensions 0, 1, 2, all the way to n-2. We were then able to generalize this result, assuming the coefficients of the matrix were Lipschitz. And here, one more time, the idea is you pick a point on the free boundary, you want to zoom in around it, see what's happening, see if there is some functional that allows us to pick up information about the function around there. And in this case, we wanted a Weiss and a monotype monotonicity formulas. These are just formulas that allow us to control what happens with the rescalings of our minimizer around a point on the free boundary. Now, everybody, we've discussed what happens with these fantastic minimizers. There's already a lot of work that is still being done, but let's understand what happens if we allow ourselves to have errors. So let me start with the definition of an almost minimizer done by Ancelotti in 83. So he considered omega minimizers or almost omega minimizers of the Dirichlet energy. So you have a domain D, you have a function in a nice space, let's say W12, and you're going to say that this function is an almost minimizer of the Dirichlet energy if the Dirichlet energy of this almost minimizer can be compared to the Dirichlet energy of any other function V in any ball, as long as V has the same boundary data as U on this one ball in which we're comparing. So if we look at the picture, for any ball that you put inside of your domain, you look at any function that has the same boundary data as you on that ball, you need to be able to compare the energies, but you allow yourself to have an error that is the omega here, and that depends on the radius of the ball. So do notice that you don't require to have less than or equal, right? The inequality changed, you allowed yourself to have this error, but we are thinking about local minimizers here as opposed to global minimizers. So there is that idea. In terms of what we require this error function to satisfy, well, we want it to be monotonic, we want it to converge to zero at zero. And I am going to assume later that this is bounded by m times r to the alpha. So it will be of the format constant r to the alpha for some alpha. So some motivations behind this idea, let me mention first of all that almost minimizers are perturbations of minimizers. So if you're looking at minimizers themselves, in real life, you're probably not going to get one, but rather you're going to have a perturbation of that. And I know Max has talked a little bit about them because he was also talking about almost minimizers for different kinds of problems. You also have the fact that if you have a constrained minimizer, for example, you have an energy and you're looking at functions with fixed volume, or even the solution to the obstacle problem itself, those can be seen as almost minimizers without the constraint. So that means that you can reframe a problem in a different way, so that instead of having a minimizer with an extra condition, you now have an almost minimizer without that condition. So also interesting because we are going to apply very different techniques to almost minimizers that might allow us to say something about those PDE problems that we had before. I also want to mention, this is going to connect to the talk that, for example, Max gave, the Altcaffarelli-Friedman energy functional. So here you have a different kind of energy, but a lot of people have been looking at almost minimizers for that energy. So there is the work of Davi and Toro, Davi and Gaston Toro, De Queiroz Tavares, Spola, Ortrey and Velishkov, the paper that Max mentioned that we wrote together, the new work that we have coming up soon. There is more by De Silva and Savin, two ones. They have the thin one-phase counterpart as well. So there are a lot of connected problems in terms of almost minimizers. There's also this work of Koblet and Zhu in the framework of multiple valued functions in the sense of Almgren. And there is also a paper of Jeon and Petrosian in which they look at the almost minimizers for the S fractional obstacle problem. So what are the challenges here of working with almost minimizers? And here there will be some connection again with the talk of Max. First of all, almost minimizers don't satisfy a PDE. And we were pretty happy with the PDEs, right? We have those techniques to apply. Here we cry a little bit until we realize there's a way to connect those techniques to ours. And the technique is we look at replacement. So in the sense of Ancelotti, where we were looking at the Dirichlet energy, what you do is you replace your almost minimizer in a ball with a function that is harmonic. So notice, it solves a PDE we love, but it has the same boundary values. So you preserve what was happening with you on the boundary, but now inside you have a function that is harmonic. And you have to use, of course, the only other thing you have, which is the inequality. It's an almost minimizer. You have nothing else to start with. So you play with this harmonic replacement, and you have to use very carefully the almost minimizer estimate. Playing with that almost minimizing estimate, you are able to control the Dirichlet energy of the minimizer, the almost minimizer, minus the harmonic replacement. And that estimate allows us to treat almost minimizers as perturbations of harmonic functions. So a lot of the technique estimates that we get from PDEs won't exactly be true, but we're going to have errors that we're going to collect very carefully from them. So in terms of the regularity of almost minimizers, I'm thinking about the Dirichlet energy still. Anzalotti in 83 was able to prove that if you have an almost minimizer in which the error is R to some power, then your almost minimizer will be of class C1 alpha over 2. I want to say a few words about the techniques he used to prove this result, because we are inspired by that to address our almost minimizers for the obstacle problem. So I'm just going to give a very brief overview of the sketch of the proof. First of all, you want to prove that your almost minimizers are almost Lipschitz. So you want them to be C0 sigma for every sigma between 0 and 1. And for that, you use some Mori space estimates. You look at your harmonic replacement in a ball, so a function that is harmonic inside, but the same boundary data. You use the fact that H itself is harmonic, so you have very nice estimates for H. Then you use the fact that U is an almost minimizer. You collect the errors that you obtain from the fact that U is not H, but they coincide on the boundary. And that allows you to get some estimate for the Dirichlet integral of U itself, with a slightly worse estimate, but the estimate is still good enough to allow us to conclude that the almost minimizer is almost Lipschitz. Then you work a little bit more to be able to prove that you are actually going to be C1 alpha over 2. And for that, you need some Campanato space estimates. Once more, you play with the harmonic replacement. You use the fact that H itself solves a PDE, so you have some estimates, the first line over here, so you can compare the gradient of H with the average of the gradient of H. Once more, you use the fact that U and H, they share the boundary, so in the boundary they are the same. You have errors from the fact that U is an almost minimizer, and with that, you can obtain some kind of estimate for the gradient of U as well, which allows you to conclude U itself is C1 alpha over 2. Okay, now let's think about how are we going to define almost minimizers for the Signorini problem. Let's remember the Signorini problem was the thin obstacle problem. So we had a region, we had a thin set that was the flat part of the boundary. That's how I described it in the stalk. And over that flat part, we had an obstacle that we had to be greater or equal to. So here we defined U to be an almost minimizer for the Signorini problem if whenever I have any ball on my region, I can compare the energy of my function capital U with the energy of any function capital V that shares the values on the boundary of that domain. We do have to require that both U and V are greater or equal to 0 in the region, the flat portion of the boundary, because this is the region in which I'm thinking I have my obstacle, and in this case, the obstacle is 0. So I have to require U is greater or equal to 0. And in this ball, if I have a V that is to be an admissible function, V has to be greater or equal than 0 in the flat portion of the ball, which lies inside of this smaller ball. Okay, that sounds great. I want to apply the ideas of Anzalotti, but there are several problems that come up here with the thin obstacle problem. Moreover, we were interested in once more considering a situation in which the manifold was not flat. So we wanted to allow ourselves to have a matrix A so that, we take into consideration those cases as well. So we are going to assume our domain is a ball, the obstacle is 0, the manifold is the flat part of the upper half ball, so over here. I'm going to assume that my error omega is bounded by a constant r to the alpha. I'm going to assume I have a matrix which is symmetric, uniformly elliptic, and notice here, I only needed to be Holder continuous, actually. I didn't need it to be Lipschitz, in contrast to what was done for the thin obstacle problem for the minimizers. Okay, so in that case in which I allow myself to have a matrix A, the definition that we used for an almost minimizer was, instead of looking at balls and functions that on the boundary of the ball were equal to my candidate almost minimizer, I looked at ellipsoids. And the reason for that is you have this somewhat natural transformation that you do because you have variable coefficients. So if for every ellipsoid inside of your region, you look at any function with the same boundary data on the boundary of the ellipsoid, which are greater or equal to our obstacle, which is 0 on this flat portion, if we have this estimate in between the energies in which I allow myself to have an error depending on R, I call my function an almost minimizer for the A Signorini problem. Okay, that sounds interesting. We are interested in what's the regularity of almost minimizers, and what can we say about the free boundary, which, as in the case of minimizers, is the boundary of the region where U is greater than 0. 0 here because 0 is the obstacle that I put on this problem, okay? So as opposed to having a variable, any kind of obstacle, you simply consider 0. You can do that by subtracting the obstacle. Now I want to mention a challenge that appears by the setup of the Signorini problem. Notice the following. You have these ellipsoids. What you want to do very naturally is consider a change of variables that transforms the ellipsoid in a ball. The problem is this transformation tilts the thin set. And the thin set happens to be crucial for the thin obstacle problem. Now, let's understand that when I'm thinking about the regularity of the almost minimizer, we're already going to have to worry about this a little bit. But in particular, when I'm thinking about the free boundary itself, it would have to be really important to understand if I have different points on the free boundary, how this tilting compare, how can I control the tilting of one point with respect to the tilting of points on the free boundary close to it. So instead of leaving this to the end, in which we're going to have to keep track of the regularity of the function that tilts the space, it's better to instead consider yet another transformation that tilts it back. And we had to be able to come up with a way to show that this function was actually very nice. So instead of looking at simply the, let's say, most natural transformation that simply transforms the ellipsoid in a ball, we want it not only to be a ball, but rather a ball in which the thin set has been straightened back to its original position. So with that, we look at a new function obtained through this change of coordinates, ux0, and that is the one that we want to understand. If I had a function that was an almost minimizer originally, what kind of problem is this ux0 an almost minimizer of? So what so happens is that if we started with an almost minimizer, if I do this specific change of coordinates that I described to you, this new function is going to not quite be an almost minimizer, but it's going to have what we call the almost Signorini property. Notice the following. I'm not saying that I can compare the energies with any ball, but rather only with balls centered at the thin space. That's actually quite important for what we do. So with this, what we do is we're going to prove that the almost minimizer will have some regularity conditions, will satisfy some, and we want to describe what happens with the free boundary. So we're going to have to look at distinct points on the free boundary, apply these transformations to both, and then we will have to compare these new functions, keeping in mind we had that more complicated change of variables, but at least the thin set has been straightened for both of them. Difficulties, as in the case of the Anzalotti problem, in which he looked at almost minimizers for the Laplacian. Our almost minimizers don't satisfy a PDE, also as in the case of Max's talk. We cannot use any explicit free boundary conditions, which is what we used in the case of minimizers, and we can only rely on comparisons with competitors, so nice functions that have the same boundary data on a ball. In the case of the Signorini problem, we shouldn't look at harmonic functions, but rather Signorini replacements. So we are looking at a ball, and we're going to replace our function u, the almost minimizer, by a function that solves the Signorini problem in that ball with boundary data u. So it will be harmonic on the upper and lower part of this tiny ball, but it's going to have to satisfy some other conditions on the flat portion of the boundary. So what we did was, first of all, prove the almost Lipschitz regularity following the ideas of Anzalotti. Let me mention that before, Gion and Petrosian were able to prove that in the case of the Laplacian almost minimizer, let's say for the Signorini problem, so if the matrix A was the identity, and assuming that the almost minimizer was symmetric, and I will talk about the symmetry issue a little bit more. So assuming that the almost minimizer was symmetric, my dog doesn't like my talk, by the way, apologize, then the almost minimizer will be almost Lipschitz. In our case, we were able to actually remove the symmetry condition, and we were able to prove that if the matrix is C0 alpha, then the almost minimizer will be almost Lipschitz. And again, the idea of the proof does follow what Anzalotti does. So we looked at this Signorini replacements instead of looking at harmonic replacements. we had to use estimates for H itself that were true for solutions of the Signorini problem, minimizers, and extract, let's say, similar estimates for the almost minimizers in which we have errors, of course. Then we were interested in proving what happens with C1 beta regularity, not across the free boundary, of course, but on the upper and lower parts of the free boundary. So in Gion and Petrosian in 2019, were able to prove this for almost minimizers, assuming the almost minimizer itself was symmetric and the matrix was the identity. In our case, we again were able to remove the symmetry conditions, and we generalized this in the case of the matrix being C0 alpha. Then we were also very interested in understanding what happens with the free boundary. So let's recall that the free boundary is the boundary of the set in which the minimizer or almost minimizer in this case is strictly greater than 0. And quite like in the case of minimizers, we also have an Almgren monotonicity formula that we can prove for almost minimizers. And that Almgren monotonicity formula allows us to classify points in the free boundary according to what that frequency is at that point. So in the case of the points on the free boundary for which the frequency is 3/2, we have what we call the regular set. And Gion and Petrosian considered this, the regular set, in the case in which the matrix is the identity and the almost minimizer is symmetric. And they were able to prove the same result that was true for minimizers, that is, the regular part of the free boundary is C1 gamma. We were able to generalize this, assuming that the coefficients of the matrix are C0 alpha, but we discovered that the correct notion for variable coefficients is not assuming that the almost minimizer is symmetric. The correct notion was quasi-symmetric. And I will tell you what this is and why we needed this and why this is the natural condition that is required in this context instead of symmetry. So let's talk for a minute about this quasi-symmetry assumption. So let's kind of think about this. For minimizers, even symmetry is actually quite important when we're using the Almgren monotonicity formula to classify points on the free boundary. I'm thinking about the thin obstacle problem. The reason for that is we need to somehow match what's the growth rate over a thick ball with the growth rate over a thin ball. Okay, if I have a minimizer in which the matrix is the identity, or if we have harmonic functions, the even symmetrization is still a minimizer. Now, this is sadly not always true for almost minimizers with variable coefficients. We actually have an example in our paper in which you start with an almost minimizer in the upper portion of the region, you evenly symmetrize it, and you can prove it's not an almost minimizer. So that shows us that symmetry is not the right idea. But of course, remember that we had that kind of interesting change of variables. So the symmetrization should occur with respect to that. And that is what we called this A quasi-symmetric condition. So let's recap. We had our ellipsoids, which we transformed into these balls after we straightened back the thin set. So there is a matrix that corresponds to this reflection across the thin space in a conormal direction that depends on what the matrix was at that point. And we define this skewed even symmetrization that is with respect to that. And this is the notion that we needed. So we defined this new function, this skewed even symmetrization, and we said a function happens to be quasi-symmetric if I can compare its energy with the energy of the skewed quasi-symmetrized function. And if that has to be true for every ellipsoid centered at any point on the thin space. With this condition, we can prove an almost monotonicity formula for the skewed even symmetrization. So notice, it's not for any almost minimizer, it's for these. And with that, we were able to follow through with our process. So we were able to prove what happens with the regular free boundary points. So those are C1 gamma. And we were also able to stratify the singular set. So first of all, in the case of the Laplacian almost minimizers, in which the almost minimizer was symmetric, Gion and Petrosian were able to stratify the singular set. And we were able to generalize that result in the case of variable coefficients, assuming our almost minimizer is quasi-symmetric. So that is the notion that is needed for the variable coefficients. So you again can stratify them. Thank you so much.